Awesome. So before we get started, I do want to mention I'm going to be I have a few problems I'm probably going to use to make a study guide of sorts to prepare for the test next week. So you guys can use that to review over and work through things. So I'll post that on campus as soon as possible if you can use that. But anyway, let's go ahead and get into this next section, which relatively I think is going to be a little bit more called than what we've kind of been learning. It's kind of been getting a lot of rules sort of together and figured out, but now we're going to be looking at a little bit more at the application of these sorts of things. So at the end of the 2.3/2.4 lecture, I kind of talked about this idea of a derivative being a instantaneous rate of change. And so this class will be a way to kind of go a little bit more into that, to maybe help, kind of attach the derivative to something for those people that are struggling to just see it as a concept. So I have a picture here drawn, and of course I'll kind of describe it. So the difference between the instantaneous rate of change and just any random rate of change of a function is, let's consider if I have 2 points, right? So obviously we know how to get the rate of change between 2 points. It's just the slope of the line between them, which we can easily find by just computing the slope, which is y2 minus y1 over x2 minus x1, right? That's something we should be familiar with. That's the slope of a line, and we can always use that to calculate the slope between 2 points, right? And that's very helpful on the line, right? Because if I just have a straight line, then that's going to be the rate. That's how it's moving. It's doing the same thing all the time. But if the function is not a line, it doesn't help us very much, right? If I took this point and this point, I found the slope between them, but that doesn't really help me to know what's happening here or what's happening here at this point, right? I kind of have an idea of what the average kind of speed or rate might have been in between the two, but I'm more interested in knowing what the exact rate is at that point, right? So for example, if you're driving a car, you're not interested in your average miles per hour. You want to know how fast you're going then, right? Because that's the speed that needs to be up with the speed limit or whatever it is, right? So in that case, when we're looking for the instantaneous rate of change, that's where the derivative comes in, because the derivative allows us to study what the slope of an exact point is. I don't have to use 2 points. I don't have to find an average. I don't have to approximate. I can get the exact rate at this particular point. So at this point, x2, right, I know that my slope at that point looks like this. It's represented by, we see there's I drew a tangent line that it only touches the curve at one point and kind of represents the slope at that point, kind of what a line at that point would look like. Okay, so again, maybe just further demonstrate this, maybe with a function that we're more familiar with. Let's look at x squared, right? So we'll have y equals x squared here, right? Now, if I take 2 points on this line, so we have the point 1, 1, and I have the point 2, 2, 4. Okay. I could try to, and let's say I'm interested in what the slope is at the 0.24, or what the rate of change at the 0.24. I could say that maybe between these 2 points that I know it kind of looks pretty close, and so I can estimate it by using a slope formula, right? So I can kind of look at the slope of the line between those 2 points. So in this case, the slope is going to be y2 minus y1, so 4 minus 1 over x2 minus x1, 2 minus 1, which in this case is just going to be 4 minus 1, which is 3 over 1, which would just be over 3. Okay, so it kind of looks pretty close on that curve. Maybe that the rate of change at that point is going to be 3. However, we don't have to just guess or approximate. I can get this exact value because we know what the derivative of x squared is, right? You can use the 4-step process or better, we can use just our derivative rules, and we'll see that y prime or dy over dx in this case is simply 2x, right? Because we pull down the 2, bring it down to the front, subtract 1 from the power, and that gives us 2x, right? So then if I want the slope at that point, I simply just plug in, because that's the x point at that value. And so that's going to leave us with 4, right? So really, as we see, this really wasn't that great of a, I mean, it's, I guess in terms of bigger or smaller numbers, it might be close, but there's still a large gap between that. And so this gives us a much better idea of what's happening exactly at that point. Okay, and that's going to become even more clear once we kind of work through some application problems, right? So I already have some of this written up here as well. I want to make some room. Actually, I'll leave that up for a moment. Let's walk through this. So whenever we're talking about movement, right? If I take, if I'm moving along a straight line, here's my starting position, and I move to this point over here, let's say, which is 5 feet away, right? So we'll say this is my starting point, then I move 5 feet away from there. And let's say here, I might be at time 2, and here I might be at, it might be time, it'll be time 0, right? So I could find kind of my average speed through that time by again, if I let the distance be kind of like my y and the time be like my x, then the speed at that point, right, is going to be the same thing as that 5 minus my 0 feet, right, over 2 minus 0, right, which would say is 5/2. So I would say that that's my average speed as I go through, right? Here's the issue. What if I don't just take a straight path there? What if I want to do something like this, right? Or maybe I want to go backwards first, right? And then I want to come back and go 5, right? None of that was present here, and my rate is going to be very different than this average rate I found, right? So we don't want to do just an average velocity. I don't want to know my average speed. I want to know the exact speed. Sorry, I can't speak. Which is my velocity. And I can find my velocity by, if I know the position of a particle, which the book often gives it as s. You might also see it like y equals sometimes. It's generally in that context. We're moving up and down like I'm throwing a ball in the air. I just take the derivative of that position and I'm going to get the velocity, right? We can also find the acceleration, right? So we can know how much I'm accelerating at a specific time by simply taking the derivative of the velocity, right? So using this instantaneous rate of change, my derivative, I can find a lot of information about movement. I know how much I'm putting into moving. I know what my speed is at that exact time, and I can also tell my position, right? So let's go ahead and take kind of all these thoughts and let's go into an example, which the book simply just says like describe the motion a lot, which really doesn't give as much clear instructions. So I kind of want to go through a step-by-step look at various aspects of studying a motion that I can do with my derivatives. Okay, so let's move this, do a bit of work. Okay, so we start off with a particle that's moving with this function. Okay, so whenever I'm at time 0, I'll get that s is at 0. Whenever time is 1, I plug in 1, and so I would get 2 minus 4, and so I get minus 2. So my position, maybe on a line, is minus 2 away. Okay, again, we can keep plugging in times and see what happens, but that's tells us the position at a given time. Okay, so we have a few questions here, and we want to kind of talk through them and understand what we're looking for, right? So the first question I have is, when will this thing when will this particle, you know, whatever it is, when will it return to 0, right? So clearly when we plug in 0, right, we're at 0, right? But I want to know kind of when it will cross that time again, okay? So let's think about this, right? What are we asking in this case? When will it return to 0? Am I asking the speed in that case, or am I asking for the position? We're asking for a position, right? So I need to use this in my S function this time, right? So if I want to know when we'll get back to position 0, I want to use this in the position function, right? And that's the position, right? So that's S. So I want to know when S is going to be 0, aside from 0, right? Because obviously we start at 0, but we may not. We want to see when we get back to that point. So I'm going to let S be 0, which is the same thing as 2t squared minus 4t. Okay. How could I solve this equation? What sort of ideas do we have? What could we do? Add 4t. Okay. So we could add 4t. And so I'll kind of write that down real quick. So if I added 4t to both sides, what would you suggest doing next? After we added 4t to both sides. Okay, so we would want to divide by t, right? Now here's the issue, which is why we want to be cautious with this, right? If I said t is 0, will that solve this? Right? If I put t is 0 in here, I get 2 times 0 is 4 times 0. It's 0, right? So if I try to divide by t, we're getting into some kind of messy territory there. So we don't necessarily want to do it that way, right? But this is a quadratic, right? We have 2t squared minus 4t, right? So we have a few methods that come to mind when we think of quadratics, right? We can factor it, we can complete the square, which most people don't like, but you should try to learn it, remember it, and the quadratic formula. Is there one of those that looks like it'd be pretty easy in this example? 2t squared minus 4t? Well, you could complete the square. I think in that case it would be 2. But let's notice, do these terms have anything in common with each other? 2t. They both are divisible by 2, and they both have a t in them. So if I factor a 2t out of both, what am I left with? Right? So we have 2t squared, I pull out a 2t, what's left? T minus 2. Awesome. And so this is still equal to 0, right? Now we have two things that are multiplying with each other, 2t and t minus 2, and that equals 0. The nice thing about quadratics, right, when we're working with these problems is that we know that if two things multiply to get 0, and one of those things is 0. You can't multiply two non-zero numbers and get 0. Okay? So that'll lead us to say either 2t equals 0 or t minus 2 equals 0. So let me think about this real quick. I might need to change some of my numbers here later on too. But we'll see why that may not work. Okay, so we have 2t equals 0 or t minus 2 equals 0. This one isn't very interesting to us, right? Because what does t have to be for this to be true? 0. Yeah, good. We're starting there, so we want to know when we return, right? So t minus 2 equals 0. What does that tell us about t? T equals 2. Good. So the answer to the question, when will it return to 0, is the time t equals 2, right? So I go to some distance back, but then I come back to 0 at t equals 2. Okay. Now, the next question is a little bit more interesting because that's going to involve, it's probably going to start bringing in this rate of change, right? Because we're asking, when will it be at rest, right? I don't know about rest in a position, right? I need to know that there was some So more momentum, some movement, right? But then it's coming to a stop, right? So there's no more movement at that current time. There's no change at that current time, right? So if I want to know when it'll be at rest, what do we think is that? So it's not the position, right? Because I don't know when I'm going to be at rest in the position. It just tells me where I'm at. But it might relate to this velocity, right? Because if the velocity is 0, you're not moving. It's at rest, right? Now the velocity might start to build up again afterwards, depending on acceleration, but at that current moment, there's no movement. Okay, so in this case, right, the first question we wanted to know when S is 0, and in this case, we wanted to know when V is 0. Okay. We don't know V at the time. Is there a way that we can find what V is? What is the velocity? It's the derivative of S. Good. So let's take the derivative of S. What is the derivative of S going to be in this case? Good. So 2 times 2, which is 4, to the 1, and then minus 4. Okay. And then if I want to know when it's at rest, right, we said we want to take this and we want to set it equal to 0. Okay. So how do I solve this? Good. Yeah. So I'm going to add 4 to both sides. So that's equals 4. And that's fine because there's no t involved in there. I'm not dividing t in that case, so it's okay. So 4t equals 4, and then we get that t is equal to 1. Right? So whenever my time is equal to 1, I'm at rest. There's no movement, right? So in other words, maybe to see this in a picture form, right? This is a parabola, right? Which it's 0 at when t is 0, and it's 0 at 2, right? So it's going to look something, the path is going to look something like this as a function. Okay, so this is s, or I'll write s of t. Okay. Notice what happens at this point, right? We start changing our direction, right? Initially, if we kind of looked at the rate as we went along, right, which I can look at the instantaneous rate of change as kind of the slope of the tangent line at each point. So actually, let me ask this question real quick. If I gave you a line and said, is the slope of that line positive or negative, what would you say? It's negative. It's going from top left to bottom right, right? And that's what's happening with each of these lines. We have a negative velocity that's slowly starting to slope off more and more. And then when it hits that bottom point, it's flat. It's not doing anything, right? Because it was negative, right? And then it slowly hits 0. Okay, so at that point, the velocity is at rest. There's no speed being applied. But when we start coming up the other side, it starts being positive again, right? The rate, we're moving up again. We're going upwards. I have to not use some word because we'll do a little bit more with this in chapter 3. Yes. Here? That is the derivative of s, right? If s is 2t squared minus 4t, then the derivative of that, right? I take my t squared term and I multiply the 2 out in front, and then I subtract 1 from the power, which will give me 2 times 2 times t, which is 4t. And then the derivative of 4 times t is the derivative of, or is 4 times whatever the derivative of t is, which is 1. And that we can use power rule there, or just like as a, just remember anytime dt over dt in that case. So that's where that came from. It would give us that t equals 1, right? But now it makes sense what we mean when it's at rest. It's basically changing. It was going one direction and now it's starting moving the other direction. Okay, so we're curious to study that point, right? Because that's a pretty important point in the parabola. We want to see when it's kind of maximum or minimum, kind of its bending point is, right? So yeah, and this is definitely a lot easier way to find that than when you had to kind of move things around, complete the square, and then you have the x point and the y point, and then you can say it, but here we can get rid of these. Okay, so next question is, what is its velocity when it returns? Right? So when it, and I guess I should say returns to 0. Okay, so we're curious to know now what the velocity is when we return to 0, right? To our 0 point. When did we say we return to 0? At t equals 2. So in order to know our velocity at that point, right, we simply just evaluate v of 2. And v of 2 is going to be 4 times 2 minus 4, right? Because I simply just plug in for t. And what's that? 4. Good. 8 minus 4 is going to be 4, right? So whenever we cross back into the positive side of things, the rate of change at that point is going to be 4. Okay. Let's see, what's the next question? Okay. What is my acceleration at t equals 1/2? Okay. So now we need to know the acceleration. How do I find the acceleration? Do we have a, right? We have a formula to find that, where you simply just take the derivative of the velocity, right? What the acceleration is doing is it's saying, okay, I'm inputting this much to grow the velocity by this much, to change its direction by whatever, right? Just like when you're driving a car, you put your foot on the accelerator to increase your speed. Okay, so if v, right, so I'll write it here real quick, it's 4t minus 4, a is the derivative of that, which is what? 4. It's just 4, right? So what is this acceleration at t equals 1/2? It's 4. What about t equals 2? T equals 7. It's always going to be 4, right? This is a constant value. That means that throughout the whole process, we are applying a constant acceleration. Okay, from the starting point, you accelerate with this much, and the velocity will start maybe going one way, but then the acceleration will slowly pick it back up the opposite direction. Okay, awesome. The next question is, what is its velocity at t equals 1/2? Right, so again, we're just going to go back to the velocity, right? So we're doing v of 1/2, which is 4 times 1/2 minus 4. What? -2. Good. Because 4 divided by 2 is 2. 2 minus 4 is minus 2. So again, this is just another example of a point to plug in, but at the time 1/2, our slope is looking something like -2 for kind of the tangent line. Okay, now that we've kind of seen some examples, right? Now we want to kind of get into describing the motion, right? So let's kind of organize a few points here that we've gathered as we've worked through, right? So I'm going to create a table similar to what the book has, and we'll kind of look at the position at a specific point, and we'll look at the velocity at that point as well. You could also put acceleration if you want, but it's always 4. That doesn't really tell us a whole lot. So aside from just knowing it, that it's going through. Okay, so let's start when t equals 0, right? We see from here that the position is 0. What's the velocity at 0? Right? We're going to come back to v of t. not 4, -4. Okay. By the way, you want to pay attention. The book might give specific units. I didn't feel like I necessarily needed to in this case, but yeah, we're just using like basic units to describe each point here. Okay, so at time 0, I have a position of 0 and my velocity is -4, right? Maybe we'll we could add in 1/2 if we want to. I don't. We can go ahead and put it on there. Why not? We said velocity was -2 at that point. What is the position at? So let's see. What's the position at that point? So we need to come back to S now, right? To calculate that. So we're going to do S at 1/2. Going to be 2 times 1/2 squared minus 4 times 1/2. Okay. So 1/2 squared gives me 1/4. 2 times 1/4 is 1/2. And then 1/2 minus 2. So that'll give us what is it? 1/2. Right. I'm going to write it as an improper fraction, -3/2, but feel free if you want to write 1/2, and that's absolutely fine too. Okay. T is 1. We get the velocity 0 there, right? Sorry, I put the velocity 0, and the position. What's the position going to be? So this shouldn't be too hard. We have 2 times 1 squared, which is 2, minus 4 times 1. So it's going to be at -2. Okay. And of course, we could keep going. Just as an additional point, I'll put 2 on there. That's going to be 0. And we saw that the velocity at that point is going to be 4. Okay. So we have a few points to kind of gauge what's happening. Okay. Now, this graph, of course, is a good, you can draw that to kind of see what the actual position function looks like and kind of guide the velocity. The book will also demonstrate an interesting graph that kind of shows our kind of back and forth position and how things are moving. So at time 0, right, we start out a position of 0, and we have a velocity of -4, right? So actually, I might move this slightly up there. Okay, so what does that mean? Well, so I'm going to let this, so this is like my S line here, and this is time equals 0. Our velocity is negative, right? So that means that kind of as I move along this S line, I'm moving in a backwards. Okay, so I should be moving in this direction. Until when? When is the particle rest? At 1, right? So when t equals 1, my position is -2. So I'm going to put that here on this picture, right? And the velocity is stopped at that point, right? It pauses, it's at 0. Okay? Again, we could put another point on here if you wish, just to kind of mark things, but I'm going to go ahead to point 2 as well, right? Or time 2, right? When we're back at 0. And my velocity is at 4. So let's see, we're going to put our starting point here, another point here, and this will be at time equals 2. We're back at s equals 0. So what does our motion look like, right? After this point, right? If I keep plugging in t is bigger than 2, this is just going to keep growing. The velocity is going to keep getting bigger and bigger, and that's going to go in this direction, right? As we saw here. So the motion of our particle maybe will look something like this, right? Where we start by going backwards, it pauses for a moment and then heads back all the way to the right. Okay, so this is kind of a good picture to describe, kind of look at the motion a little bit, where you're going. Once again, we can mark more points if we need to, but this is the general idea we need for the movement, to know when we're going back and we're going forward. Okay. So that's all in all, really, it's just complete analysis of a position function, right? We don't necessarily always have to ask every question here. Not every question may be of interest, but this is a good kind of thorough look at what sort of questions we're asked and what we're interested in, to know when we're going to be returning to a point. Especially, I think there's some homework, and I'll probably definitely have a practice problem or two where it's going to be like a height instead. So we want to know when the ball's going to land back on the ground and how fast it's going to hit it and all that. But here's kind of a good look at a instantaneous rate of change in terms of velocity and accelerations. Any questions on this? Question? Yes.
How'd you get 4 again for the acceleration?
So that is the derivative of the velocity, right? The velocity is 4t minus 4, right? As a function. So when I take the derivative of it, right? The derivative of 4t is just 4 times the derivative of t, which is 1, and then the derivative that goes with it. So it leaves us. Any other questions? Yes.
You changed on the what is the acceleration? You changed that from 1.5.
Yeah, I actually did that on the velocity too. The reason I did that is because I had it at 1, right? But 1 was the time that the velocity was at rest. I didn't want to do that point in particular. I wanted to just pick another random point. So that's why I changed it. And I just figured I'd have those line up. So apologies. Any other questions?
So we find the position of the particle in time with that equation right there.
Yes. Yeah. So everything you need is going to come from this equation in some way, shape, or form, right? You can get if you want to, if you come to a problem like this, you might just say, okay, let me go ahead and get the velocity and the acceleration right now, and then I'll answer every question. Okay. And then you want to pay attention to what you're being asked, right? So we know what exactly needs to be 0, what function we're using in order to evaluate this. Any other questions before we move on? This is kind of the big idea of this section. Everything else are just more examples of an instantaneous rate of change and other kind of disciplines. So maybe run through a few of those. Or yeah, however many. Okay, so make some room here. More things. Here, okay. So other examples that you'll get are definitely won't be as involved as that one, just because it'll just be a quick run over. It's just so I'll give a kind of a couple examples that are in the book. So they just say the area of a circle, right? That's an oval. Something. Okay. The area of a circle, right? If depending on whatever the radius is pi r squared. Right? And so a question might arise and you might say, okay, let's suppose that I have this circle, but I want to change its radius. I want to kind of change its size continuously, kind of make it bigger and bigger and bigger. Okay. Then you want to see, well, what is the rate of change of that area look like in each case? Well, you just apply the derivative to this function, right? I'm saying I'm changing the radius, so I want to know how much the area changes with respect to the radius. So I just need to find the derivative of the area with respect to the radius, which is going to be pull that on 2. That's pi. Okay, right? Because we're doing the derivative with respect to r squared. with respect to R, sorry. Pi is just the constant, right? Don't get that confused. For those who have worked on the 2.5 homework, there's a few where they'll put in some pi or square roots and try to trip you up. But remember, those are just numbers. Okay. So this is the rate of change in my area with respect to the radius, right? So this is a real quick example, but a lot of the, I would encourage you, if you have time, you can go and look at the other book problems and kind of practice those, but a lot of them are just along these lines where it says, what is the rate of change with respect to this variable with this variable? Okay. And then it also gives an example of we have a sort of device that has a voltage that it outputs that's dependent on the temperature put into the system. So the voltage in that case would be 390 T plus, I'll just do, I'm not gonna worry about doing all the exact decimals, but they might give another example like this, okay? And they'll say, well, you know, what is rate of change of voltage with respect to, I'll just write W or T, temperature, and then it might give you a certain point, but we'll just leave it here for now so we're not doing anything too crazy, right? So all you need to do, right, if we're asked for a rate of change, and give derivative. Instantaneous rate of change we want to go to the derivative of this thing, right? So this is our voltage. It's with respect to the temperature, right? If the temperature changes, then my voltage is going to change. It's dependent upon the temperature. So we simply just need to find dV over dt. What is dV over dt going to be in this case? Plus 2 times 0.005, which is actually the same thing as 0.01. Since it's a lot simpler to do. Good. So that would be the question. And then I think in here it says that when the temperature is 50 degrees Celsius, then you would put 50 degrees in and calculate that out. Okay, I would never on a tester quiz give you a problem where it's kind of some wacky number and calculate it out. You can use your calculator, but always good to kind of check your answers. Okay. They give another example, same thing with kind of a voltage and an inductor for anyone who's kind of interested in the electrical engineering side of things in some way, shape, or form. You can read that in the book. It follows along the same pattern. You're given a function, it says what is the rate of change whenever it's this value, right? So then you would take the derivative, and then if it gives you a certain number to plug in, you plug it in. And that's what the question is going to be. Okay. Last thing I want to talk about, last example, I guess is a little bit more involved, but not too much more. So it's in terms of a cost, right? So we can also use this sort of language in this talk when we're talking about income and how much things are charged, how much we're getting out of it, right? And so if I have a cost function, right? So I think they use, so they have, for example, 2,000 plus 6x plus 0.01 x squared. Okay. What this says, right, is it says that in this case, x here, number of products produced. So essentially, if I'm running a business, right, and I'm gonna make this many objects, right? It's gonna cost so much to, to make that. And so there's this initial cost of 2,000, right? And then 6 times these units, 0.01 times squared. I'm not sure exactly how some of that might work out, but this is basically telling you how much it's gonna cost to produce 5 items or 6 items, 7 items, right? And a lot of times, most businesses aren't just making like 5 items at a time. They're making hundreds, right? Thousands at a time to be able to ship out to places. And so we can always, again, like with these examples, we can take the derivative of this thing, right? dc over dx. What's the derivative of this going to be? Awesome. Yeah, so the 2,000 just drops, right? We have a 6 left over and 0.02 times x. Okay. But this is essentially, this actually has more meaning than just, this is the rate of change with respect to x, right? Because these numbers, because they're relatively small, what we see happen is that as this continues to get bigger, right? This actually is really close, right? So I think the book says like, so if I produce in items, okay, n's a really big number, okay? If I want to look at the rate of change of that, what's called the marginal cost. This is actually, this number here is going to be extremely close to this quantity, right? Essentially taking the cost of the n plus 1 item, so maybe the 1,001st item, minus the cost of the 1,000th item. Essentially saying that this marginal cost is essentially the cost of producing another item, right? So if you're considering adding another item to make something, you can easily just look at the derivative to give you a good idea of how much that additional item is going to cost. So this is kind of the sort of thing I'm trying to. I assigned a problem like this one and see what they determine the average cost of producing n units and the marginal cost of producing the n plus first unit. So this is kind of the sort of thing we're talking about, right? So you can find the exact derivative, and you can also use that to say that's the approximate cost of producing the n plus first unit in that case. Cool. I don't really have too much to say other than that. So we'll go ahead and that's basically the end of that lesson. I would encourage you to do that. So we have a couple options. I can either, if you want, I can go ahead and start on, just do a real quick start on the next section. And in that case, when it comes to Monday, I might have more time, we can review and practice problems. Or I could do some, maybe like go over some problems from the quizzes and stuff, or kind of talk about those. Is there a preference? Do you want me to, okay, sounds good. Yeah, absolutely. Do you want me to talk about like the ones that are on here, on the last one? Okay. Good. No problem. Okay, so I want to ask, by the way, I don't think I saw it, but I want to make sure. Did anyone try to do the 4-step process for number 2 or 3? Okay, I didn't think so, but I wanted to make sure it was clear that the first one was the 4-step process and the other 2 weren't. Okay, those would be really hard to work through if that was the case. So the first problem was the